Hi, I'm Ben-Yaakov. This presentation is entitled Instability and Oscillations of Inverters and Converters Bus Capacitor, Part 2. I'd like to thank Stas for the great lab testing and measurement. Part 1 is here. This is the link to Part 1. I'm also going to print it at the page of the YouTube video that you are now watching. So the problem is related to problem of oscillation of capacitor, bus capacitors, and I'm showing here a real measurement of a system, 50 volt battery, high power. We see here the phase current, we see them distorted. The phase current are measured here, distorted due to the oscillation. We see the bus oscillation here, the voltage on the bus, and this is a 5 volt per division, so it's quite a bit, and then it's growing. And if not stopped, then probably it would have damaged the system. So it's a real problem, and we have here a bus made of ceramic capacitors. In part 1, I've shown that inverters and converters do have a negative input resistance, and that this could bring about oscillation, and I've also laid out the mathematical foundation to understand all the relationships involved. In this part 2, I'm going to talk about instability in practical systems and then to point to possible solutions. So here I'm starting off with a simulation of a buck converter. This is a hybrid model, it's LT-Spice based. It's hybrid because on the one hand I have a operational amplifier, on the other hand there are some behavioral sources. For example, here, rather than having switching transistor, I've put here the average voltage at the midpoint of the buck converter, and then also I'm expressing the current that will be reflected to the input through a dependent source, which is a behavioral source. So this represents a case of a buck 5 volt power loading. Here we have 5 volts on the bus, stabilized to 5 volt, and the load is 5 ohms. So it's 1 amp, so it's 5 watts. So this is the buck, and the purpose here is to show that indeed, if you change the input voltage, here it is superimposed and AC superimposed on the DC of 10 volt. As the voltage goes up, the current will go down if it is a constant power load, because if the load is constant, the power of the load is constant, then if the input voltage going up, then the current should go down. So the product of these two is the power that is delivered, given the efficiency, of course, which I'm not considering here. I'm also showing the output voltage, which is 5 volt. What about the incremental impedance? This is done by running an AC analysis here and looking at the current and the voltage, AC here, dividing the voltage by the current. And here is what I'm getting. This is the amplitude and this is the phase. This corresponds to minus 20 ohm. Why is it minus? Because we have a phase of 180 degrees, okay, as expected. And let's just quick check to see if the numbers make sense. It's a 5 watt system. The incremental resistance is VI over IR, and I is P over V, and therefore it is 0.5 amp, and therefore the incremental resistance is minus 10, which is the bus voltage, over 0.5, which is minus 20 ohm, exactly what we measure here. Notice that the incremental resistance corresponds to the bandwidth, that is the control or the phase compensation that you have in the network, because when the loop gain drops below 0 dB, then you lose actually the ability to control the output, and therefore you cannot maintain a constant power. So this is actually the point of loop gain being 0, the bandwidth of the control, and beyond that the impedance is going up, and of course the phase is now changing to be positive because it's going to be actually looking at an inductor with the phase corresponding to it. Okay, so one has to bear in mind that this whole process, all this concept of negative incremental resistance is relevant within the bandwidth of the control. So now I'm coming to the real problem. Here we have an inverter, we have a motor. This is a cable. The cable has a inductance, and therefore we do have a situation of an inductance of the bus capacitor and the incremental resistance of the inverter or converter, okay? And as I've shown in the first part, you can convert this to the parallel combination here. And here are the rules here. This is the conversion between the RP and RC. This is this one here. And the definition of the quality factor. And then we know that the oscillation will commence if RP, this one, is larger than RE. That is, in order for the system to be stable, RP has to be smaller than the absolute value of R input, that is the incremental resistance of the converter. It's quite interesting that when I sort of worked out this relationship, I come up to a conclusion which is very important, and that is this RP, this parallel equivalent resistance, is equal to L over C RC, and C is the capacitance, RC is the resistance, this is the ESR as a matter of fact, and this is actually the time constant of the capacitor. So the RP is L, which is the cable inductance, over the time constant of the capacitor. So in order for the system to be stable at high power, you'd like this time constant to be large. If it is small, then RP is large. It's one over the other. It's very interesting. So you need a large time constant, which means that the dissipation of the capacitor is large, and this is why it's more stable. So it really makes sense. So this time constant again is the capacitance times the ESR. So if you have a case in which you have a number of capacitors which are parallel, they do have the same time constant, because the capacitor is times n, the ESR is over n, and the product is the same, so it really does not matter. The condition doesn't change if you parallel the same type of capacitors. Like the same conditions is relevant to one capacitor as well as many capacitors of same type connected in parallel. Very interesting, kind of intriguing. So now I'm comparing two capacitors. One is a ceramic capacitor and electrolytic capacitor. They are chosen sort of for the same type of current that you choose them. Obviously here you'll put some in parallel. And what we see that the time constant of this ceramic capacitor is 50 10 to the minus 9. For the electrolytic is much larger, 16 10 to the minus 6, and the ratio is 300. So we can already see, although we're going to go into it in more detail, we already see that ceramic capacitors are more prone to instability because of the lower time constant. So let's now take a real example and see what all this means. So I'm considering a case of an inverter with 500 amp ripple current. This is a ripple current that has to pass through this capacitor. And it's a 70 kilohertz, that's a ripple current itself, the low frequency part of it, of course. And the input cables connecting a battery of 50 volts. So this is the system we're going to consider. So I'm going first of all to consider a ceramic capacitor. So it seems that 4.7 microfarad, 100 volt seems to be a good choice. And it turns out that this capacitor can carry 2 amps with 15 centigrade rise in temperature, which is sort of okay. So if each capacitor is 2 amps, then I need 250 capacitors. Unfortunately, this capacitor loses its capacitance when biased. So a 100 volt capacitor at 50 volt, this particular one, will drop to 1.5 microfarad. So it's going to be a smaller capacitor. So now 1.5 times 250 is 375 microfarad. And now I'm going to ask what is the voltage ripple due to the current ripple considering this capacitance. And it turns out it's 3 volts. That's quite a bit. So therefore I'm going to increase the number of capacitors from 250 to 750. So the ripple will be 1 volt, which is kind of reasonable. And then I find that the total capacitance is now 1.125 millifarad, which is also reasonable for 500 amp ripple. What about the ESR? For this particular capacitor, it's 11 milliohms, and therefore the resistance of all these capacitors in parallel is 15 microohm. I'm going to take 20 microohm considering the interconnection, etc. So I have now a bulk capacitor of 1.1 millifarad, 20 microohm, and the time constant is 22 10 to the minus 9. So again, doing the calculation of RP, and I find that this system will be unstable with a power level above 37 watts, very little. So to confirm this, I'm running here a simulation in which we have an input cable. This is the inductance. This is the bus capacitor. And here we have a dependent current source which emulates a constant power. This is done by defining the current as P, which is the power, over the voltage here, so that the product of I times V is P. So the I will adjust itself to be constant power. So now running it, I see that at 20 watts, it's stable. Obviously I have oscillation because the Q of the system is very high. So with the step you do from 50 to 51, you have quite a bit of an overshoot, but we see it's going to die out. On the other hand, if I run it at 50 watt power level, it is clearly unstable because now the amplitude is going to increase, and of course this is an indication of a unstable system. Now what happens if I add here a resistance, and I've chosen like 100 microohm, which kind of makes sense for very high current. And in this case, I find that at 220 watts, it's still stable. But this is although stable, but it's pretty close now already to instability, so the effect is not that large. Now what about electrolytic capacitor? So I'm now choosing a capacitor for this particular case, and here are some aluminum electrolytic capacitors. I'm choosing this one for 70 microfarad, and it has a 0.34 ESR, and then the time constant is 16 10 to the minus 6. Notice that for this whole family, the time constant is, well, it's changing, but not that much, okay? So for a given family of capacitor, even though the capacitance is going up, then of course the ESR is going down, so it sort of keeps, this is the time constant in 10 to the minus 6 of a second. So again, I'm doing the calculation of how much power can I run the inverter to the point of instability, and I find first of all the RP now is much lower, 94 milliohm, and the power level is 26 kilowatt. That's a lot. And also I'm doing here a calculation of what is the total capacitance and the resistance, which is for the parallel unit, which comes to be 200 microohm. And here is the simulation, 70 millifarad, 220 microohm. This is the same inductance, and I'm running it now for 25 kilowatts, and you see that it is stable. Well, it's kind of close to instability, but it's still stable. On the other hand, for 40 kilowatt, you see very nicely that it really going up, because as we've seen, the limit is 26, so I'm quite a bit above it. So everything seems to be compatible one with the other, the simulation with the derivation, which is approximate, I should say. These are not very rigorous calculations, but I think for practical purposes, they are good enough. So the question is, what can we do? Well, obviously, putting a large resistor here or a small resistor here will help, but these two cases are not practical, because if I put here a large resistance, then of course we'll have a high power dissipation due to the fact we have a high current here. And here, I cannot put just a resistor here because it's going to short. It's going to be a small resistor, like 100 milliohm. We need small resistance in order to combat the small value here of R sub I. So therefore, it's going to short out the bus. So this is not practical, but we can sort of modify it using decoupling elements. Here I can put a capacitor for decouple the DC voltage. And here I'm going to put the resistor in parallel. I really don't need this inductance, but the point is that this is a cable. So you cannot put on a cable just a resistor. You have to have a long wire to the two ends of this cable, so therefore you're going to have a inductance. So I have to take this into account. So let's start with this solution. In this case, what I want to do is to have a resistance around the resonant frequency of this circuit. That is, resonant frequency due to L and C, because this is the critical range of frequencies. I don't care about the lower frequency, it could be capacitive, that's okay. At a higher frequency, obviously, I'll have the resistance, which, as we'll see later on, is kind of a problem because it's going to dissipate power. But the point is that the crossover point here, in terms of the frequency ranges, is that I want this branch to be resistive around the resonant frequency of L and C. Okay, so this is what I want here. And then I want that the parallel combination of Rp, of this capacitor, and this added resistor and Ri, this parallel combination will be positive, so the system will be stable. Now, Rp usually, this is the reflected resistance, will be usually much larger than this one because I want high power and Rp is for low power. So therefore, I can cross this. So this is the requirement. I can sort of rewrite these requirements in terms of the resonant frequency, as I've said, saying that I want the breakpoint of this couple, the RCP and RCP, to be below 1 over LC. That is, I want the breakpoint at which resistive here to be below the resonant frequency, so that at resonant frequency it will always be resistive. So this will be a constraint that I have to take into account for choosing the capacitor. Okay, this capacitor, this is the constraint for choosing the capacitor. So I'm going to run it, and here it is. This is the original capacitance, the ceramic capacitors in parallel, the cable, the damper, and here is what I see. Without the damper, at 50 watts, it's already oscillating. We know that 36 watts is the limit. And here with damper, it is running at 26 kilowatts. Well, you see it's a bit unstable. The safe limit would be like 20 or 22, but obviously 22 compared to 50, this is another domain. And now I'm going to show this in a real simulation. This is again the buck converter. This is a buck converter which I've put for this purpose, which is in closed loop. And then we have, here is the damper. And first of all, I'm going to run it without the damper and then connect it and see what's the difference for this particular case. And you see the 250 watt, the whole thing is oscillating. Again, there's a lot of sinusoidal signals here. And here I see what happens when I have the damper at 250 watt. There is an overshoot here. By the way, we can see the effect on the output. This tells us something about the control, how tight is the control, and you see that we get about 35 millivolt jump here, which is pretty good. This is a between 10 and 11 volt step, and this is for 250 watts. Another issue that we have to take into account is the fact that this resistor is going to dissipate some power at high frequency, because then the capacitor is shorted. There's no DC, but there is a ripple voltage, and we have set it to 1 volt. So therefore, this 1 volt will cause a current, and this current, of course, will cause dissipation depending on the design, and this is not going to be negligible. It's going to be in the watts region, depending on the power level and the voltages, etc. Now, one more point I like to make is that if the damper is made up of a number of capacitors in parallel, then usually you'll have to have another resistor in series, because the ESR here will be just too small. So you have to add it, and this is the resistor usually that will get hot. Now, what about this option here? It's kind of nice. It means that you need to run another wire and then put a resistor in it, and this is the implication. I have never tried it, but theoretically that's what it is. And to understand how it works, let's just remember that the input for AC is a short. So therefore this point is in fact connected to ground. Here it is. So it's doing the same thing as before. We are just putting a resistor in parallel here to the RP, and that's the same thing. However, here the requirements are a little bit different. I want this resistor to be effective just about the resonant frequency, and then at higher frequency I really would like to have the inductance, which is blocking here, so that at the ripple frequency the impedance here will be high and the current will be low. So I want around the resonant frequency to be resistive, this network here, or this I should say, and then I want above this frequency, that is at the ripple frequency, I like it to be inductive, so it will block the current. Okay, so these are the requirements. And here I'm running it with this LT-Spice schematics, and here it is. I find that for this particular choice of parameters, I can go up to 15 kilowatt. I've calculated the current to be 140 milliamp, which is not that much, but this is actually taking into consideration the fact that this is like a short. In fact, it's not. So the voltage across this branch is not the ripple as compared to ground, because usually there is some remnant of the ripple here, so the voltage drop is lower, but this will be sort of the worst case. But there are some limits here. And again, this comes out because of this frequency requirement, that we want the time constant of this to be larger than the resonant frequency, and this brings about this relationship. What does it mean? It means that LP has to be small. You cannot have it large. You like to have it large because then it will block the current here, but you cannot have it because there is this restriction, and therefore there is a limit to what you can do. And if the inductance is too high, this will not work. So maybe a combination of this and the capacitive damper is a good choice. So let me just wrap up here with some major points that we've shown here. We've shown that ceramic capacitors are really causing some instability, and that the model developed in this presentation can help, I think, the analysis and damping of the bus capacitor oscillation. Now, there are some issues that I have not discussed, which are important, and that is, for example, the combination of ceramic and electrolytic capacitor, how to deal with this situation. Also, the newcomers, the solid or hybrid electrolyte capacitor, have different characteristics, so we need to see how do they fare with respect to this oscillation. And also I have not touched on active damping, that is with the control. This is a subject by itself. Hopefully I'll prepare a presentation on that in the future. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.